So that's what we did last time. I think we were at this point, we talked about individual I/O devices, their speeds and how their speeds are different. That means that their hardware is so different. Most of they are our communication devices. Of course, they are either they take data from the computer or they provide data to the computer, but their speeds are so different and their technologies are so different. So their software must be different also, including the hardware. I/O is very detailed, as I said last time. Operating systems, most of the operating system code, we talked about 80 million lines of code for Windows 8, right? Most of that code comes from the I/O devices, drivers, and the handling of I/O and etc. So they occupy lots of space in an operating system footprint on a computer. Okay, so let's go back and let's start our discussion on the principles of I/O hardware again. This is our basic conceptualized computer system. We have our computer CPU, okay, at the center, and the CPU is connected to the system bus. This is system bus, okay. The system bus transmits data between the various computer components, mostly between CPU and the other I/O devices. And the CPU is connected to the memory and the other stuff through the MMU, memory management unit, and they all communicate on this bus. In this case, it's a very simple picture, like a simple bus, but in reality, it is not. It is not as simple as this. For our current desktop computers or the server computers, things are a little bit different, but conceptually the things are here. Okay, every input output device connected to a computer
Sir, I think you froze.
No, I am not frozen. My connection is frozen. I am okay, thank you. um, every every I/O unit connected to a computer has a mechanical part like the monitor screen and a controller. Okay, this controller is the part that is in the computer system. It is connected to the system bus. Okay, and this controller knows about the monitor itself, and it knows how to communicate with the rest of the system. The same controller, keyboard controller, is for the keyboard, and there is a USB controller that is responsible for responsible for communicating between the computer and the USB devices. And we have the same thing for the hard disk controllers, scanner controllers, mouse controllers, and etc. So for all the devices that were connected to the computer, we have an electronic part, electronic hardware part, which is called the controller. Okay, so I/O is often consists of mechanical components and electronic components. Okay, and as operating system designers, of course, we don't design these I/O units, we don't design these controllers, but we need to know how the controllers work so that we can write I/O software for our operating system that can communicate with these devices. So basically, this is how the devices communicate with the rest of the computer. For example, let's look at this video controller. This video controller is a electronic device, is a digital device, of course, and it has some registers in it. Let's say this is register A, register B, register C. Okay, what are the meanings of these registers? It depends on the controller. Okay, and for the video controller, maybe I will have a large buffer, screen buffer. Okay, this is a buffer, the screen buffer. For the basic non-graphics related buffers, okay, this is a just 80 by 40 byte buffer. Okay, so it's a matrix. Whatever you write to this buffer, it is shown on this monitor. Okay, if I write 65 as the first element of this buffer, this video controller is responsible for showing a character A at this position. That's the responsibility of the controller. Okay, so this is how you communicate with the devices. You write to special buffers and special registers inside these controllers from the CPU. You write these, and the rest of them are handled by the controller. For the keyboard, for example, if you say that, let's say this is the register A of this keyboard controller, if you put a special code in it, let's say I put a special code 12 in this A, that means that I like to read a character from the controller. I'm just making these up. Okay, and then the keyboard controller is responsible for getting a keystroke from this keyboard or whatever keystroke is provided to you by the user, and it puts this data in here. Let's say that I got this value FA, whatever it is. Okay, so basically this is what you do. You write to these registers, buffers, and you read from them. Okay, this is how we communicate between the CPU and the input-output devices. And the meaning of those registers and the buffers are, of course, they depend on the device itself. That's why they say that the interface between the controller and the device is often very low-level one. Okay, we don't know the details, and in fact, knowing the details about those, the meanings of the registers and the buffers is a low-level information, and we don't like to know about them for most of the operating system. Okay, we like to isolate all kinds of details from the programmer. Okay, so this is how we communicate between the CPU and the rest of the system. As I said, this is a very simplified picture. Nowadays we don't have this picture, but we have, here is a more realistic picture that I took from Wikipedia. Okay, our CPU is here. This is kind of the system bus, but the system bus is divided into two parts: the north bridge and the south bridge. North bridge is basically the faster part of it. It is responsible for functioning as a hub between the CPU and the memory slots. Okay, memory, because communicating with the memory should be very, very fast. So there is a special path here between the CPU and the memory. It goes through this north bridge. Yes.
I think north bridges are absent in current motherboards. If I remember it correctly, the type of north bridge is in the CPU itself, and we don't have any need for north bridges in the motherboard.
Well, from time to time it changes, but that's not. Well, I mean, for some of the CPUs, there are libraries running. Okay, they say that we are going to run this library anyway. We are going to run this video processing library anyway, right? So why don't we make this part of the CPU itself? Well, we don't call it the CPU, but you make it like this is the CPU, okay? And this is the communication part. These are the libraries. These are the deep learning stuff, and etc. This is a chip like a computer, but CPU is here. So this is a conceptualized picture. But that doesn't mean that we don't have these kind of main boards, motherboards on computers. For example, this is a modern motherboard where I have the Northbridge chipset as a separate entity, and it gets very hot. That's why they put a very large sink on it. Okay, and my CPU is here. Okay, so as I said before, this is a very simplified picture, and the current modern variations are different, but one of them is this. Okay, so I mean, don't get surprised that they put all of this stuff in a single chip and they call the CPU, but CPU is in fact just part of it. Okay, just part of it. And that doesn't mean that, that doesn't mean that they are selling you a single chip and they are calling it CPU. That one includes the CPU plus other stuff. And if you like to draw the pictures, if you like to design an operating system for that environment, you have to be aware of these buses. Okay, so there is a separate. Okay, let's assume that there is nothing in it but just the CPU, like this picture. Okay, and there is a separate line here, and that connects to the memory slot. Also, graphics card is so important. The CPU has to communicate with the graphics card in a very fast way. I have another path here, and the rest of the I/O devices, of course, they are important, but they are not. They don't have to be as fast as these memory and the graphics stuff. Of course, we like them to be fast, but it gets very expensive to provide these kind of specialized buses. So I have this Southbridge controller here. Okay, so and then I have my PCA slots, and I have my USB buses, hard drive buses, and etc. Okay, but if we go back, this is the main picture. Okay, this picture did not change from the 1960s much. Okay, in effect, we have our CPU, we have our I/O devices. They all are connected to the same system bus, and all the I/O devices use some kind of a controller to communicate with the rest of the computer system. Okay, so we said that the CPU communicates with the I/O devices using these registers, but how does the CPU write to those registers? Okay, how does the CPU write to those registers? We don't know the answer to this question yet. Let's talk about that. Okay, I/O. As I said before, each controller has a few registers that are used for communicating with the CPU, and we need to write to those registers, and you need to read from registers, also the buffers. How we are going to do that? There are two ways of doing it, and which way you are gonna do depends on your hardware. Sometimes you use one, sometimes you use the other, sometimes you can use both of them. Okay, the first one is the I/O port space method. Okay, in this case, in the I/O port space method, the CPU provides you with the special instructions: in instruction and out instruction. With the in instruction, you provide your register name, the CPU register, and you provide the port number. Okay, port number corresponds to the address of this register. Okay, here, this one or that one or that one. You say that I am going to write this number to this port, and how are you going to write it? I'm going to write it whatever I have in this register. Okay, that's for writing. For the end, this means that I am going to read from this port number, and whatever I read is going to go to this register, CPU register. So this is how you read from a controller. from a controller. When you start reading from a controller, that means that your CPU is communicating with the I/O device. Why? Because that data comes from the device itself. Okay, for writing to the device, you use the other special instruction. So that means that if you are going to use this I/O port space, you need these special instructions. If those instructions are available, you use them. For some systems, these instructions are not available. What do? Those kind of systems use memory mapped I/O. Okay, memory mapped I/O. Okay, uh, what is a memory mapped I/O? In this case, the system maps all the control registers into the memory space. Let's say if this is my memory, okay, I started from address 0000. Maybe the top part of the memory, F, B, C, D, some address, high address, okay? If you write to this address, the system maps this address to the I/O devices registers. So whatever value you are writing to this address, it is directly written into the devices registers. Whatever you read from this address, it is directly read from the devices registers. That's why we called memory mapped I/O. Each control register is assigned a unique memory address, okay, to which no memory is assigned. So whatever you are reading or writing regarding this address is not related to memory. It is directly from the device. Okay, it is directly from the device. So for these kind of input-output operations, you don't need special in and out instructions. You could use any type of memory access, direct access, indirect access, whatever. Okay, and it looks like this is much more flexible than the I/O port space. Why? Because I don't have to use special instructions, and I could use any type of addressing that I like. Okay, so as a programmer, I may prefer memory mapped I/O over the I/O port space. But as always, if two things are available for you, there are pluses and minuses. Okay, what are the pluses for memory mapped I/O? I don't need the special I/O instructions. Okay, I don't have to use them, and my CPU becomes less complicated because two less instructions means that less complicated CPU. But there are some downsides for memory mapped I/O, and we are going to see it in a few minutes. Okay, but for many people, some prefer one way, the other prefer the other way. Sometimes the hardware is more simplified for one way. Okay, some computers, some CPUs, some computer systems provide this. They both provide the memory mapped I/O. Also, they provide I/O ports. So this is I/O port space. Your memory is different from the I/O devices registers. This is just one whole address space, memory mapped I/O. This is the hybrid one. Okay. As always, we are not going to go into the details of how the things work in hardware because it's not a hardware course. We need to know hardware good enough so that we can write some software for it. We can understand how we can communicate with these kind of I/O devices. Okay, so for us as operating system designers, or for people who study operating systems, we need to know that these are the two main ways of communicating with the I/O devices. Memory mapped I/O, as I said, advantages. Okay, we don't need the special instructions for the memory mapped I/O. And with memory mapped I/O, no special protection mechanism is needed to keep users from performing I/O. Why not? Because We assign those pages as system only pages, and that's it. Okay, and with memory mapped IO, every instruction can reference the memory anywhere in your IO devices on your memory. So those are the advantages, but the disadvantage is this. Disadvantage is this. Okay, slightly more complicated system bus. Okay, simple one, a slightly more complicated one. What did we say? We communicate with the memory through some special bus, whether you call it North Bridge or something else, doesn't matter. Okay, so this makes things faster. So the problem is, okay, the problem is if you communicate between your CPU and the memory using the special bus, and if you are doing the memory mapped I/O, then there should be a mechanism saying that whatever the CPU is trying to access is not in the memory, but it is in the I/O device, because I am using the memory mapped I/O. When I say read this address from me, okay, somebody should be able to tell you that, okay, this address is not in the memory but is in the I/O. Okay. Uh, Previously, I didn't have this problem because the same system bus is listened by both memory and the I/O device. When CPU wants to read something, and if that address is in the memory answers it. If it is in the I/O device, then the I/O device answers it, and this problem is solved. In this case, it is not going to happen that way. Okay, CPU only issues those addresses in this memory bus, and I/O devices don't know about that at all. So your hardware becomes a little bit more complicated because whenever you need to read something, you need to read something. Somebody has to make a decision that that thing is from memory or the I/O device. Like this North Bridge here. Where is North Bridge? Okay. Sometimes when you say I need to read something using the memory mapped I/O, okay, this memory controller hub make the decision. Okay, this is coming from the memory bus or the I/O devices. So it makes this chip more complicated. So that's one of the main disadvantages of the main disadvantages of the memory mapped I/O. And the other thing is related actually. Caching becomes a problem because caching is handled by the memory management unit. Okay, when you read something from the memory, it either comes from the cache or from the memory itself. But if you have everything in the cache, the things becomes very, very fast. The problem becomes this. What if the thing you are trying to read is from an I/O device and your memory management unit is trying to cache it? Okay, I am trying to read something from the I/O device, and your memory management unit, which is in here, right? MMU is here, and your memory management unit is caching it. What is the problem with this picture? If you cache the data that you read from I/O device, it's a huge problem. What is the problem?
You can't update it, or you have to go back through the bus to update it.
So caches are complicated enough. Yeah, you can do that. I mean, you have to update the data anyway for the memory too. I am not talking about the cache becoming complicated. I'm talking about caching I/O device data is very dangerous. That's what I'm talking about.
Malicious hardware, maybe?
No. By the way, I don't know what malicious hardware is. There is no malicious hardware. There is malicious software.
We can create malicious hardware.
That's very difficult to get your malicious hardware to a system. Somebody has to buy your malicious hardware and install it. And again, whatever malicious it is, okay, however malicious it is the software that does it. Okay, anyway, so what is wrong with caching your IO data, IO registers, IO buffer. Think about what I am reading from the IO space, IO device. Why do I read from IO device? Think about this as being a keyboard, okay? This is a keyboard. IO has registers in it. The IO controller has registers in it.
Sir,
Yes.
is it because if we cache them too much, the IO we won't be able to get any more data from the IO device, or it will always load the older ones because it has already cached it.
Exactly. If you make a cache of this data in your cache, okay, if you keep a copy of this data in your cache, if this register changes, the cache doesn't know about it, because cache assumes that your memory will not change if you don't update it. But in this case, your memory location is being changed by this device. So if you cache it, then you keep reading that data from the cache, from the CPU. It is going to be fast, but whatever you are reading is not updated. It is outdated data. Okay, you keep reading the same thing in a very fast way. So somebody has to know about this. Somebody has to say that don't cache the IO data. Don't cache the IO address space. Okay, so this makes the caching a little bit more complicated. Or since I am using the memory mapped IO, this is my memory. This part of the memory belongs to the IO devices. So if this is a page, in your page table, remember in your page table entries, there was a 1-bit entry. It is cacheable or not cacheable. Okay, so you say that this page is cacheable or not cacheable. I have to use a single bit to represent this issue. So that makes my whole memory management unit more complicated. Okay, remember in C we have two special modifiers. When you say register int A, and we say volatile int B. What is register? Register says that keep this A in your register. It's going to be read very fast. When you say volatile B, okay, volatile B, this means that don't keep this B in your registers. Don't cache it, because this B belongs to an IO device. An IO device will keep changing this B, and every time I refer to B, read it from the memory itself. Don't keep it in the register. Okay, so that's the reason why they introduced these two special keywords for the C programming language. Okay, good. So that was the disadvantages of memory mapped I/O. But these disadvantages are for the system only. As users, we don't care about them. We just use our regular memory access, instructions to read from the I/O devices and to write to I/O devices. Caching and complicated system buses are dealt with by the hardware, with the help of the software, of course. Okay, any questions about this disadvantages of memory mapped I/O? I guess there is not. Okay, remember what we are doing. We are talking about the principles of I/O hardware. Okay, so first we looked at with the principles of I/O hardware. We looked at the system bus and we looked at how we communicate with the I/O devices. Okay, two ways of doing it, and we looked at our system buses and etc. Now we are going to look at this special communication technique between our system and the I/O devices, which is called direct memory access DMA. Okay. So once your data is ready in your I/O device controller, let me erase these. Okay, let's say this is our hard drive. Okay, as an operating system, I asked this device, I said that, okay, I am going to, in your special registers, okay, in this register I said that read, okay, block number 1005 blocks. That's what I said. And put whatever you read into this special buffer. So when the I/O device makes all this loading for the hard drive, all the data is ready in this special buffer. As CPU, the interrupt happens, right? When the data is ready, interrupt happens. As the CPU, I stop whatever I was doing and I started running a special interrupt handling routine. Now operating system had the control. Now operating system has to transfer all this data one by one from here over the system bus to special place in the memory. Okay, so I am doing this one by one. This is the interrupt handling routine is doing that. Okay, so this is a very simple operation. All I am doing is reading from one place from the memory and writing to another place in the memory, because I am assuming that I am using the memory mapped I/O. Okay, but that takes valuable CPU time. While I am doing this, all the other processes are waiting for me to complete this simple transfer. The idea is, this is a very simple operation. Why don't we design a special device which sits on the system bus, okay, and it is called the Dma controller. And the responsibility of this Dma controller is to transfer this data from the I/O device's special buffers to the memory. When this operation is done, the DMA causes an interrupt, okay, telling the operating system that the transfer is complete. That's what the direct memory access is. Okay. So the DMA is a special controller. It sits on the system bus like the others, and it has access to the system bus independent of the CPU. And partially it acts like a CPU, but it's a very small CPU. It cannot execute all kinds of instructions. Most of the time, all it does is transfer some data from one part of the memory to another part of the memory. That is, from the I/O device to the I/O device controller to the memory itself. Okay, so that's called the direct memory access technique. And for direct memory access, you need to have this special controller in your system, DMA controller. And of course, for complicated systems such as this one, DMAs become more complicated, and usually you don't have a single DMA device. Okay, you have multiple DMA devices, so that you can do multiple transfer operations at the same time. So that means that many things can be done at the same time by this DMA chips. Okay. The DMA controller, because it's a controller, right? It's a controller. Since it's a controller, it has its own registers. Okay? And CPU writes to these registers to tell the DMA that I have started an I/O operation. Your task is to transfer the data to the memory when the I/O operation is complete. And tell me when this operation is complete. Okay? So this is how you communicate with the DMA chip, like a regular controller. Okay? The DMA controller has several registers. Okay? A memory address register, byte count register, and one or more control registers. Okay, you say that when the data is ready, you are going to write to this location. Okay, and the control registers specify the I/O port to use or the memory location to use, and the direction of the transfer. Okay, the transfer doesn't happen one way only. Okay, the transfer can happen from memory to the device buffers too. For example, if you are writing to the hard disk, you tell the DMA that, okay, transfer all these bytes to the hard disk controller for me. Okay, and this operation is done one byte at a time or one word at a time, etc., depending on your system structure. And this makes I/O operation a lot faster. Without the DMA, this is what happens. Okay, the disk controller reads the block from the drive serially, bit by bit. Okay, until all the data is read. When the data is ready, the controller causes the interrupt when the data is ready. When the interrupt happens, the CPU stops whatever it is doing, and it starts executing interrupt handling routine, and that interrupt handling routine uses the CPU to transfer this internal buffers data to the memory. Okay, so operation is simple, but it takes time because we are taking the CPU's time to make this transfer. With the direct memory access, this is what happens. The CPU programs DMA to load data. Okay, first the CPU tells the hard disk controller that it needs some data, and it gives the data's address. Okay, I need this block from the disk, and the size of the data is this much. Okay, so the CPU starts the I/O itself, but then it tells the DMA that I have started an I/O operation. The data will be ready at this location. Okay, whenever that data is ready, you are responsible from moving that data from this location to that location in the memory. Okay, and whenever that data is ready, hard disk controller tells the DMA controller that the data is ready, and the DMA controller initiates the transfer by issuing a read request over the bus to the disk controller. Okay, and this is the picture actually. First, the CPU tells the CPU tells the disk controller that I need this much memory, I need this much data from this address, and then CPU programs the DMA. Programming the DMA means that you are writing some special code to these registers. Says that, okay, you are going to transfer this much memory, okay, from this address to that address when the data is ready. Okay, when the data is ready, inside this buffer, the DMA request transfer to the memory, and this memory happens. This transfer happens in a loop. Okay, so I am reading these bytes one by one to the given address, one by one. Okay, when this operation is done, then we provide an acknowledgement to the DMA, and the DMA tells the CPU that I am done. When this operation is done, then that means that the data is ready. Whoever is waiting for that data now can be unblocked, can be put in the ready queue so that they can use the CPU. They can be rescheduled again. Okay, good. Any questions about this DMA operations? So basically they have invented this CPU, they have invented this DMA access to release the CPU from the task of doing this transfer by itself. And this is going to make our CPU more this is going to make our CPU available to the more specialized processing of the processes, and my CPU doesn't have to do this straightforward byte transfer from the disk controller to the main memory. What is the downside? What is the disadvantage? The disadvantage is your system becomes more complicated. Now you have a DMA controller to worry about, and you need to write special software for this DMA controller. Okay, and this DMA controller has to be protected, right? Our ordinary processes should not access this DMA controller. Ordinary processes shouldn't know about the DMA controller, so it has to be protected. You have to write special code for it, and your system becomes more complicated and more expensive. So that means what? That means if your CPU is not very expensive, if your CPU's time is not that important, then you don't need the DMA actually. I mean, if you have an embedded system, and your task is just a single task and you are not doing anything else, okay, all you are doing is running some special code, a single program computer, okay, running some special code and doing some transfer between main memory and the disk controller, and you have nothing else, then you don't need the DMA, because while DMA is transferring your data, if your CPU sits idle, then you don't need the DMA. So for some embedded system, many embedded systems, you don't have the DMA controllers. Okay, so I think there was a question.
I wanted to ask, so DMA is like a secretary in an office. They tell him, go fetch this paper while I'm doing something else and notify me when the paper is ready.
Exactly, yeah, exactly. Both ways, okay? Go fetch this paper or write this paper. Okay, so yeah, and they don't know the meaning of that data, and they cannot do much. All they do is just transfer from one place to another place, which takes time for anybody. Okay, and if your CPU's time is important, then you keep that secretary. If it is not that important, I mean, this is an expensive part of the system, then you don't add this device to your system. Okay, good. Any other questions? Okay. Again, still we are doing the hardware. Let's go back a little bit. We talked about this interrupts, but we are going to talk about it again, because interrupts are important parts of the input output. Let's talk about the interrupts again. Like the DMA interrupt controller, there is a device named interrupt controller, and it sits on the system bus again. Okay, it sits on the interrupt system bus again. It's a specialized controller like the DMA controller, and the interrupt controller task is to get all the interrupts from all the I/O devices and tell the CPU that there is an interrupt happening. Also tells the CPU that what kind of interrupt it is, okay, so that the CPU knows the type of the interrupt, and it tells the operating system that this kind of interrupt is happening, and the operating system has a special routine for that kind of interrupt. Okay, when the disk finishes loading some data from the disk to the device's controller, it tells the interrupt controller that, okay, the data is ready. And the interrupt controller takes this information. Interrupt controller takes this information and it issues an interrupt. It calls an interrupt for the CPU, so that the CPU knows that there is something happening that has to be handled. And CPU takes this information. Also, CPU takes the information from the interrupt controller about the type of the interrupt. It is important to have this information because disk interrupts are different from keyboard interrupts or the clock interrupts. Why? Because there is a different routine. Because there is a different routine to handle different kinds of interrupts. And the CPU acknowledges the interrupt controller saying that, okay, I got your interrupt request and I am handling it. I am handling it. This interrupt controller can handle many devices. Okay, if there are more than one interrupts happening, it can handle that too. It can put them in a queue. Okay, as soon as the interrupt is acknowledged, the interrupt controller can issue another interrupt if there is another one. And this interrupt controller can prioritize the interrupt between these devices. Okay, so it has some logic in it, and it has a controller. Now we are going to look at the details of this interrupt operation. Okay, but I think before I start doing that, maybe I should take a break for 10 minutes. Let's be here around 11:30 and we will continue from this point. 10 minutes of break.
See you in 10 minutes, sir.
Okay, so let's talk about interrupts again. I think this is the third time we are talking about interrupts. Um, when the I/O device, okay, interrupts are caused by the I/O devices, and that's it. The CPUs don't cause interrupts. When the CPU causes the interrupt, that means that I am executing a special instruction. That would become a trap, right? So that's how we do the operating system calls by trapping to the operating system. So when the interrupt is caused by the I/O device, we call them interrupts. Okay. When an I/O device finishes the work, it causes an interrupt by asserting a signal on a bus line that has been assigned. So there is not a single interrupt line. There are many interrupt lines, and similar devices are connected to the same interrupt line. The signal is detected by the interrupt controller. Okay, and this interrupt controller, as we say, this is a controller. It's a special device, and its responsibilities we talked about. Okay, the controller puts a number on the RDS lines, specifying which device needs the attention. Okay, so the CPU knows it knows not only the interrupt is happening, it also knows the address of the device causing the interrupt. Okay, then when the interrupt happens, when the CPU stops whatever it is doing, okay, the CPU says that, okay, I am going to use this special interrupt handling routine to handle this interrupt. It has a table somewhere. It's called it is called interrupt vector. Okay, inside this interrupt vector, it has the addresses of different interrupt handling functions. Okay, interrupt number 0, 1, 2, 3, 4, 5, 6 goes that way, like that. Okay, for each one you have this A2, B0, F1 is the address of the interrupt handling routine 0, then 1, then 2, then 3. So who populates this table? Of course the operating system does. Operating system populates this table at the system boot up time, and when the interrupt happens, when this CPU says, okay, interrupt has happened, I am stopping whatever I am doing. Okay, I'm going to save some important registers like the program counter and the program status word, etc. After saving those, it just takes this address and it jumps to it. Okay, now the operating system has the control. Operating system code has the control. Okay, shortly after it starts running, the interrupt service procedure acknowledges the interrupt is taken. I am handling this interrupt now. Okay, it can continue whatever it wants to do with the interrupt. Okay, the hardware does a minimal part. Hardware is the hardware. All the hardware does is it gets the interrupt, it stops whatever it is doing for the CPU. It saves only a minimal amount of information. Okay, and then you provide an acknowledgement to the interrupt controller saying that I got this interrupt, I am handling it right now. Okay, the rest of the stuff is handled by the operating system's interrupt handling routine. Okay, this is what we have seen before. I just repeated it again. In fact, the second time we have seen it, it was more detailed than this, I guess. Okay, so let's look at it. So why we suddenly started talking about interrupts again? Part of the interrupt and part of the hardware, but interrupt handling doesn't happen this simple all the time because we don't have computer structures, instruction execution structures like this simple. We have the pipelining. So with the pipelining, things are more complicated because your instruction execution doesn't happen in a single clock cycle. Okay, you fetch your instruction, you decode it, you execute it in the simplest term in the pipelining, and you overlap many instructions depending on your pipelining structure, depending on how many consecutive stages you have in your pipeline. Okay, so that means that if the interrupt happened, you are not executing a single instruction, you are executing multiple instructions, even for the simple pipeline case. If you have a super scalar CPU like this, you have multiple fetch decode pipelines, and you have many execution units. So that means that two instructions, 3 instructions, up to 10 instructions are being executed at the same time. And each one is at a different phase. So what are you gonna do with these kind of structures? When the interrupt happens, are you going to wait for all the instructions to be executed? Or you are going to just stop whatever you are doing and you come back when the interrupt is handled? That's the difference between the precise and imprecise interrupts. Okay, let's look at those definitions. Okay, so with the precise interrupts, it is the first case. You wait until you cleared out all the instructions in your pipeline. So when you are done with your instructions, okay, you will say that my program counter is at this address number 316. Before address number 316, I have executed everything, and after I am done with the instruction interrupt handling, I will start with this address. This is the precise interrupt handling. So you wait until your whole pipeline is empty. There is nothing to do in your pipeline. Maybe that might be a good solution for this kind of system, but if you are doing this kind of system, you have to wait at least 10 instructions are executed. When 10 of them are executed, you can handle now the interrupt, but that means that your interrupt will be handled in a delayed way, and we don't like delaying in handling of interrupts, because interrupts are important. That's why we are interrupting the CPU. Okay, so what is the solution? The solution is you leave some of your instructions halfway executed. Some of them are fully executed, some of them are not executed at all. So this would be the case. Okay, you will say that the instruction that I had at 304 is only 80% executed, 308 is only 60% executed, 324 is 10% executed. Okay, so when you are saving information about your current state, saving the current program counter is not enough. You need to save all this information somewhere in your system, so that when the interrupt is handled, when you come back, you can continue from this point on. Okay, so imprecise interrupts are more efficient in terms of responding to your interrupt requests, because you can immediately stop whatever you are doing and you can start handling the interrupt. But they are more complicated in terms of interrupt hardware, because all that information has to be saved by the interrupt hardware. Previously, all I said was the program counter and the program status word and the stack pointers and etc. Just 3 or 4 specialized registers. Now I have to save lots of information about at what stage each instruction is in my pipeline. That is more complicated, imprecise. Okay. For the precise interrupts, okay, PC is saved in a nonce place. All instructions before that point, okay, before the PC I know that they are all fully executed. No instruction after the PC has been executed, I know. Okay, an execution state of instructions pointed by PC is known. Okay, So before I start executing the handling the interrupt, maybe I will wait until all the instructions clear the pipeline, or maybe I should do some undoing. Okay, okay. Maybe some parts of the instructions are partially executed. I am not going to wait for them, but I will undo whatever they did. Okay, that's one solution. That's the precise interrupt. With the imprecise interrupt, okay, you usually store lots of information about the current state of the CPU, including all the pipeline stages. Okay, that's a very large amount of information. You put them in some place in your special place in your memory, so you can go back and restore your current state. Okay, and unfortunately, all that information has to be decoded by the operating system, and it is the responsibility of the operating system to solve this complexity of restoring the CPU state after the imprecise interrupt handling. Okay, and the code necessary to restart the process that is interrupted is very complicated. Okay, so there is always two sides to stories. We like imprecise interrupts because they are very responsive in terms of handling the interrupts. Okay, and they are efficient because you are not wasting any part of the undone or completely done parts of the instructions, but they make your operating system complicated in terms of saving the interrupts. And writing more code is not a problem. You write the code once, and that's it. But writing more code means that there is a possibility of introducing more bugs to your system. Okay, and this is a very important place in your operating system handling the interrupts. If you introduce a bug in your interrupt handling routines, that's going to be bad. That's almost certainly a crash of your system. Okay, good. So any questions about precise and imprecise interrupt handling? Okay, no questions. So we are almost done with principles of I/O hardware. Let's look at some of the principles of I/O software. Okay. We had to know about the details of I/O hardware. Now, there are some common issues with the I/O software. Let's look at them. Okay. The goals of the I/O software. What kind of software should we write for the I/O devices? Okay. So these are some of the common goals. Device independence. Nobody should write code specific for some I/O device. I mean, if I am opening a CD-ROM file, I shouldn't be writing specialized code for that. Okay, opening a CD-ROM file should not be any different than open a network file or opening a USB file or open a hard drive, physical hard drive file. Device independence. Okay, so my code should always be the same regardless of device, the technology of the device or the drivers. So that's called device independence. Uniform naming. Okay, I should not use different names for different devices. Okay, I think last time I showed you here, I have an SSD on this computer, my computer, and I have connected a USB device. Okay, for the Windows the naming was the same. Their file system types were very different. One of them was anti-file system, the other one was FAT file system, I guess. But the names of the files are exactly the same. I can copy files from one device to another device, okay, and my naming did not change at all, okay. In Windows, this is a little bit different. Why? Because for different devices we use different letters like that, okay. C is a specific device, D is another device. That's kind of violates this rule for Windows, but for Unix, all the devices, all the storage devices at least, are are part of this root directory, and under the root directory I have all kinds of directories like mount, USR, source, and etc. Whatever file system you have to mount under these directories. So that makes the uniform naming like it is meant to be. Okay, so that's what we mean by uniform naming. Okay, all the files should be named simple by string or integer, and they should not depend on the device in any way. Error handling. Okay, what did we say about the file systems or the I/O devices? We said that the code for the I/O devices are detailed, complicated. Why? Because there are many types of I/O technologies, and different I/O technologies cause different error cases, and we should be able to handle all types of errors, whether it's if you are trying to open a file to write to on a CD-ROM, or if you are trying to open a file on your screen so that you can read from it, etc. Weird stuff. It cannot happen. So there should be ways of handling these errors in a uniform way. And if the error can be handled without letting the user know that there is an error happened, then it should be done that way. Okay. The upper levels of IO software should not know what kind of errors are happening. Okay, good. Some definitions: synchronous I/O and asynchronous I/O. Synchronous I/O is this in synchronous I/O, the CPU in asynchronous I/O. So let's look at this one. In asynchronous I/O, the CPU starts the transfer. Okay, you say that as a CPU, you say that I want this data from hard disk. Load this data from hard disk. Okay, since I know that this is going to take a while to load this data, I am going to do something else. Okay, and I am going to wait for my interrupt. This is called asynchronous I/O. Okay, this is called asynchronous I/O. With the synchronous I/O, you wait until the data is ready. That's why it is called synchronous. Okay, so as users, as programmers, we think that we are doing synchronous I/O. Okay, why do I say that? Because when I say print f something something, and then scan f something something, and then in a for loop I do that and that. So as a user, I think that when I issue this function, I wait until it is done. Then for the scanf function, I wait until the user provides some data, and this for loop and etc. So this is an input-output operation, this is an output operation, and this is an input operation. As a user, this is my assumption, but in reality, these things are happening asynchronously. Why? Because when I say printf this, okay, there is a system call happening, and while that system call is happening, maybe I am blocked. Maybe I will wait until that system call is handled. Okay, but I am assuming that I am waiting and I am keeping the CPU. No, CPU is doing something else. Under the hood, asynchronous I/O is happening with these operations, but as a user, I am assuming that the things are happening synchronously. Okay, I issue, I wait. I issue, I wait. Okay, the CPU is not doing anything, but in fact, CPU is doing many other stuff, many other stuff. Okay, as a regular user, there is no way that I should say that. Okay, this is going to happen asynchronously. What do I mean by that? This is going to happen asynchronously. When I say scanf, okay, I shouldn't be blocked. I know that scanf is going to take time. While you are working on it, let me continue executing some instructions. Let me continue executing some instructions. And this is sometimes provided to the ordinary users. Some operating systems make asynchronous I/O available to users due to performance issues. Sometimes this is provided, but in that case, the user should know that two things are happening at the same time. So it's kind of multi-threading operation. Okay, so this is about synchronous and asynchronous input output. And very often used technique for the input output is buffering. Okay. Uh, Often when you are reading your data, you cannot put your data in the final destination. What do we mean by this? Maybe this is a good example. Okay, as a regular user, I like the string to be printed on the printer. Okay, so I put this data in a special in my user buffer, and I issued a system command saying that send this data to the printer. Okay, often we copy this data to our special buffers in the kernel space. After I copied them, I start printing them to the printer. Okay, so I end up having two copies of the same data on my system. Seems inefficient, but sometimes this is the only solution. I think we talked about this when we talked about the paging, right? Do you remember why we need such a buffering strategy? What is the problem of printing this data directly from the user space? Do you remember those?
Not to create a lot of context switches, just gather everything that's going to be printed and print it at once.
You don't need the context switch here in this case because when you are in the kernel space, okay, you are in the kernel space and you are free to access anywhere in your memory, including the user space. To access the user space, you don't need the context switch. Context switch means that the control is in the kernel or control is in the user. When you switch to kernel, you are copying this data from this position to this position. So you are accessing the user space anyway. So don't I keep, why don't I print this data directly from the user space to the printer? We talked about this when we talked about we talked about this when we talked about paging. Anybody? Just take a guess. Try to make a connection between paging and this issue.
It is slow to print. That's why we don't do it one letter at a time.
I never said that we don't do it one letter at a time. We do it one letter at a time. Doesn't matter if it is from the user space or kernel space. Did I say we don't do it one letter at a time? You have this string and you ask the operating system to print this string, and the operating system prints the string. That's it. The question is, why do I need to copy all that data to the kernel space? Why can't I print them directly from the user space? Okay. Of course, to access the printer registers, I need to be in the kernel space, but why do I have to copy all that data to the kernel space?
Is it because we need some system calls in order to print that string?
Yeah, so I would make those system calls and use the data from the user space directly. Why do I need to copy all that data to the kernel space? I am running in the kernel space, that's fine. I have to run it because for the printer, for me to use the printer, for me to use the printer controller's special registers, okay, I need to be in the kernel space, that's true, okay, I need the special privileges. But my data doesn't have to be in the kernel space. My data could be in the user space. So I take the address of the user space data and send this address to the kernel space, okay, kernel to the operating system. And the operating system runs and it prints each letter one by one. Instead of using this data, it uses this data. That's what I am asking. Why do we need to make a buffer of it? A second buffer.
To ensure that the user doesn't change it while we are copying it.
Yeah, that's one thing. Yeah, of course. Yeah, the user doesn't have to but the user is blocked anyway, right? The user is blocked. But you are saying that maybe it's a multi-threaded application. Maybe the other threads might be changing it. That's one thing. That's true. Okay, that's good. What else? The other thing is this. Our paging system might think that nobody is using this user page for a while, right? Nobody is using it because its user is blocked, and it's going to wait until this page is printed. So it may swap out this page. When the kernel needs it, the page is not there and it's going to complicate stuff. Okay, plus other stuff like Osama said. So in order to have these kind of problems, solve this problem for all, okay, you make copies of this kind of buffers. Okay, I make a copy of this kind of a buffer, and after that I print this string, knowing that nobody is going to modify it, knowing that it's going to be in my memory all the time, because it's going to take some while to print this out, because each character is going to take some interrupt. The printer is going to tell you that I am ready, give me some more, I am ready, give me some more, etc. Okay, so that's why we said that buffering, okay, is a very frequently used technique in operating systems. You buffer the same data many times. In this case, it is 2 times. Sometimes you need to buffer it 2 or 3 or 4 times at different places. And we are going to see why at the end of this chapter, I guess. Okay. So let's look at this case, actually, this printing stuff. Programmed I/O, okay? It looks like I am using the CPU to do this input-output stuff. I am going to write each character one by one. It's called programmed I/O as opposed to direct memory access. And this is how it is done. with the programmed I/O. Okay, this is what the kernel does. It copies the buffer, okay, from the user space to my kernel space with this amount. So this is simple byte copying. Okay, this is like mem copy. P is the kernel buffer. Okay, I copied my buffer from position buffer to P, and then in a loop from 0 to count I do this. Okay, this is printer status register, address of the printer status register. Remember, this is my CPU and this is my printer controller and this is the system bus. This printer controller has registers in it. One of them is printer status register, and I am checking this printer status register if it is ready or not. If it is ready, okay, I am going to write this character to this printer data register. So I had used two registers on the printer controller. One of them is the printer status register, the other one is a printer data register. Okay, so this is my printer is very simple. If the printer is ready, I can put a character, simple character, to its buffer, just one character, and I wait until the printer is ready again. So this is called busy waiting, as we know before, and this is the simplest I/O that you can do without using any interrupts, without using any DMA stuff. And when it is done, I am done with the printing stuff. I can return to the user. Of course, this is wasteful in terms of CPU time utilization. Why? Because here I have a loop. It is waiting for this register to be available. Okay, of course this one is using memory mapped I/O, right? Memory mapped I/O. At the beginning of this program, okay, somebody said that printer status register is 0x A2B17A. Somebody gave this address, okay, to this pointer. Now I am accessing that pointer. I am checking if it is ready or not. So this address, of course, depends on the controller, the printer controller. Different printer controllers have different status register addresses, data register addresses. Okay, that's the part of the device driver. Okay, so this is the simplest that you can do. Busy waiting. We don't like busy waiting much in terms of CPU utilization. So what are we gonna do? The next idea in I/O is, if you don't like busy waiting, what would you do? If you don't like busy waiting, if you think that busy waiting too wasteful in terms of CPU time, what would you do?
Block it with a semaphore.
Who is going to who is going to unlock the semaphore?
When we can make it, when the device is ready or sends us a ready signal.
What do you call that ready signal? How does this device doesn't have a process. Device is not a process. How could the device send you a ready signal? Your idea is right, but you're not using. Say it again, Furkan.
Can we use condition variable in order to check if it is ready or not?
If you are using any inter-process communication functions, devices, etc., you need to have two processes, two threads, okay? This is our thread. Where is the other thread? The device is not a computer. Device is a device. It doesn't run the device controller doesn't run a process or kernel, a thread. You cannot use inter-process communication mechanisms to communicate with the device. Device is not a computer, it's not a process. If you don't like busy waiting, the answer is interrupts. Okay? You don't wait until the stated register is ready. Okay? You wait until the device causes an interrupt. Okay? You wait until the device causes an interrupt. That's what we are going to do. Okay? It takes CPU time. If each character takes 10 milliseconds to print, that's like eternity for a computer. Okay? I am going to wait 10 milliseconds. Okay? So 10 milliseconds is more than enough time for me to context switch and do some other useful work. But how am I going to come back? I will come back when there is an interrupt. The interrupt is going to tell me that, okay, I am ready, I am done. The printer is ready. So this is the interrupt-driven I/O instead of busy waiting. So again, I copy the data from the user space to the kernel space. I enable all the interrupts. This is kernel code, okay? I can enable the interrupts. And first, I wait until the printer is ready at the beginning. When the printer is ready, I put my first character and I say that, okay, I'm going to go to schedule something else. I am not doing a busy waiting here, okay? So this is how you start your printing data. And then when the interrupt happens, this part starts executing, okay? If count is 0, remember this one, I say that, okay, I can unblock the user now because everything is ready. I printed everything. Otherwise, I put this PI into the printer data register. I decrement the count by 1. I increment I by 1. And I tell the printer that I acknowledge the interrupt. And I return from the interrupt. Okay? I return from the interrupt wherever I was interrupted. Okay, so that's it. So this is the first part of the kernel routines. This is how you start your printing stuff, and this is how you do it one by one, character by character. Every time you print a character and you don't run into a busy loop, you go back to interrupted process. Okay, and your original process that asks you to print the string will be unblocked once you have consumed all of your data. Question for you. How do you know that your printer is ready before you put your data into the printer data register? How do you know that? See, I have waited until the printer is ready. Here, I did not wait until the printer is ready. How do you know that printer is ready? Furkan, say it again. I didn't understand what you said.
Is it something about device driver? I mean, the driver of printer cause some interrupts or something else like that?
Yes, exactly. This is why we are called, right? This is the interrupt handling routine. This part. Interrupt happened because interrupt is telling me that the printer is ready. I am running this because the printer says that I am done printing stuff. I am ready. Okay, I am causing an interrupt. Okay, it caused an interrupt. I know that the printer is ready. I put my character. Okay, I tell the printer that I handled the interrupt and I return to the interrupted routine. Okay, I am not returning to the original process that asked me to print something. I am returning to some other process here because that process is still blocked because I did not print everything. Okay, so this is interrupt driven IO. This is programmed IO. This is interrupt driven IO. Okay, so the advantage is it doesn't waste any CPU time while waiting for CPU to print something, but it takes some time to doing context switching because every time interrupt happens, you have to stop your process, you have to save lots of data, you have to load lots of data to handle this interrupt, and you have to go back. So two context switchings are happening for every time I need to print a character like that. Okay, but it is still better than waiting for 10 milliseconds because in 10 milliseconds I can do two context switchings and more useful CPU executions. Okay, good. So this is the interrupt driven IO. It is much better in terms of handling the CPU time, but as we said before with the DMAs, this is a very simple operation. Why don't we do this using our special controller, Dma controller? I would start my printing operation like that with my CPU. Every time interrupt happens, okay, every time the printer says that I am ready, my DMA chip is going to transfer this PI to the printer data register. If I do that, then in that case, my CPU will not be interrupted. Okay, it will be interrupted only if everything is printed, and I will save lots of context switch time. That's called the DMA. And with the DMA, okay, with the DMA, the controller feeds the characters to the printer one at a time without CP being bothered. Okay, so in essence, the DMA is doing my programmed IO. DMA is doing this. DMA is doing this for me. Instead of CPU doing this, DMA is doing this. DMA says that, okay, if the printer is ready, I am going to put it. If it is ready, I am going to put it. So it is doing whatever I am supposed to do without using any CPU time. Okay, this is the code for the DMA IO. I copy from user space to the kernel space. I set up my DMA controller and I block the current process. Okay, when the DMA causes an interrupt saying that, okay, I have printed everything, I say that, okay, I handled the interrupt, I am unblocking the user and I return from the interrupt. So this is all I am spending for the CPU time. It looks like it is very efficient in terms of CPU. Okay. Okay, so this is simple enough. That doesn't mean that this whole operation is simple because somebody has to transfer all those bytes from the kernel space to the printer. In this case, DMA is doing it. So if we are wasting any time, we are wasting the DMA's time, not the CPU's time. Okay, CPU's time is more important than DMA's time, and most of the time there are many DMA devices available, and I can do more than one DMA operation at the same time. That's fine if you have this kind of nice
In a
CPUs.
CPU, you have a multiple DMAs.
Sure, yeah.
Okay,
We don't say that CPUs have multi DMAs. We say that the computer system has multiple DMAs.
yes, of course.
Well, in fact, it's a single DMA chip, but it can answer many tasks at the same time. Because all it is doing is not, I mean, transferring some data from memory to devices, right? It is not doing any complicated memory addressing. It is not doing complicated arithmetical operations or that kind of stuff.
Yes, but it's still doing the things that usually take the most time, right?
Yeah. So if we are wasting any time, we are wasting the time of DMA. And in fact,
Yeah,
inside the DMA might be using interrupts too, because if the printer is ready, printer is going to issue an interrupt. That interrupt is going to be handled by the DMA chip. So even for the DMA, we are not wasting any DMA's time, and we are not causing any context switches for the CPU because the interrupts are handled by the DMA.
I see. I see. So the CPU usually just gets the DMA's interrupts and
Yeah.
acts upon these.
CPU say that DMA, this is your task. When you are done, just interrupt me. So CPU is doing two things. This is your buffer. When you are done, just inform me. That's it.
I see.
Okay, so these are the some DMA interrupt related issues about the IO software. And IO software, structure of the IO software, it is designed usually this way. At the bottom we have the hardware. Okay. On top of it we have the interrupt handlers. These are very low level operating system structure. Okay, operating system routines. Interrupt handlers have to be written by the operating system, and different types of devices have different type of interrupt handlers. Okay, and interrupt handlers are usually parts of the device drivers. Okay, device drivers for the hard disk device drivers, SSD device drivers, network stuff device drivers, etc. They are written by the device designers. Okay, and they are provided to the operating system, and they handle the device related stuff. So the device drivers know the register locations. Remember what I had written here? Okay. The printer status register, this address is printer status register, and I take this address of sign here. Okay. So this address is known by the device driver. Since that device driver is written by the device manufacturer, that person knows this address very well because they designed it. Okay, so this is part of the device driver. This is part of the device driver. On top of the device drivers, now you have device independent operating system software. Okay, so what do they include? For example, for the open function, right? For the open function needs to find the file, open it. If it is not there, create it, permission, etc. They all have to be handled. Okay, they make calls to the device driver. The device driver knows the details of how the things are done on the physically on the device itself, but the device independent operating system software doesn't know anything about the device itself. That's why they are device independent. They don't know if they are working on a USB device or the hard disk device or network device. Doesn't matter. And then we have the user level IO software. That means that the function that we are calling, the function open, we call that function, that's the user level function. That function makes some processes, and if it needs, it makes a operating system call. So this is how the things are structured in terms of handling IO operations. Okay, so we looked at these, okay, and now we are going to look at these two layers in more detail when we look at the um, uh, IO software. Okay, I think I'm going to stop here, and we will once more look at this interrupt handling, because I think these two slides are provided by the book. To go parallel with the book, I am going to go over these 10 steps of handling the interrupts, and we are going to look at this picture. Then we start talking about the device drivers, and I am hoping to finish with this chapter, not tomorrow, but maybe on Monday. Okay. So how many weeks do we have now?
I think we have 2 weeks, sir.
Including this week?
No, excluding
Yes.
it.
Okay, good. So my plan is,
Are
fi-
we,
my plan
are
is,
we now on 13 weeks?
No, I think including this week, we have 2 weeks.
really? Oh,
Yes.
okay,
So
anyway, I think I couldn't do one or two classes. I will do extra classes and I will finish up with this chapter and I will barely skim over the deadlocks. I don't like talk about deadlocks because deadlocks is not part of the operating systems anymore. Nobody is handling them. But I like to talk about some security and virtual operating systems. Um, and after that we are done. Okay. I am going to assign one more homework for you. That's going to be about I/O and file spaces, file systems, and that will be your fourth homework. Okay, I'll see you tomorrow.
have a good day, sir.
You too.
Have a nice day, sir.
Thank you. You too.